In this capsule on carbocations, we will look at the different types of carbocations. Just for brush up regarding the different types of carbons in a chain, watch the previous video in the series Stability of Carbocations. I have written a small compound, which is propane here. This compound here is propane, a 3-carbon alkane. Notice all carbons are sp3 hybridized. And we have, in the previous video, we have seen that the CH3 carbon and the CH3 carbon are called primary carbons. Why? Because this carbon of the CH3 is connected to just one other carbon, directly connected to one other carbon. For example, C1 is connected to C2. That's it. And C3 carbon here, C3 carbon is connected to C2 carbon. So carbon 1 and carbon 3 are called primary carbons. And carbon 2, which is connected to C1 and C3, it's directly connected to two other carbons. So carbon 2 in propane is called a secondary carbon. And notice the hybridization of these carbons here. C1, C2, C3, all of them are sp3 hybridized carbons. Now, with that background, let's move here to this structure here, ion. Notice notice the difference between propane structure on the left and this carbocation, which is called a N-propyl carbocation, or this propyl carbocation. Notice the positive charge on the end carbon. Positive charge indicates the loss of electrons, as we know. So, and it indicates loss of an electron. So, carbon 1 of this chain has only 3 bonds and an empty p orbital. So, there is a p orbital on this carbon. In the carbocation carbon, there is a p orbital. There are no electrons in that. It's empty. Okay. So, and that carbon is connected to just one other carbon, C1, where the positive charge is connected to just C2. So this is called a primary carbocation. And likewise, carbon 2 in the bottom structure, carbon 2 is the secondary carbocation. The secondary carbon. The secondary carbon, in this case, it has a positive charge, and this is called an isopropyl carbocation. That's the name of the carbocation, but this is the secondary carbocation. Again, this carbon 2, the central carbon with the positive charge, that has an empty p orbital. So keep that in mind. We'll come back to why we are saying empty p orbital. Of course, lack of electrons makes it empty. But now let's just look at the hybridization of these carbocation carbons. So previously, when we talked about hybridization, we talked about number of electron domains around the central carbon. Here, this carbon, for example, in propane carbon, known as primary carbocation, has 4 single bonds, 3 of them to hydrogens and 1 to carbon, and the hybridization is sp3 hybridized carbon, and the geometry, molecular geometry, is tetrahedral because it has 4 electron domains, right? 4 bonds. In this case, though, there are only 3 electron domains. This carbon here or this carbon here, it has only 3 electron domains, which are, for example, in this carbon 1 here, the 3 electron domains are the 2 CH bonds and 1 CC. So 3. And the 3 electron domains, the best option for those 3 bond pairs or electron pairs is to keep the optimum distance between them to minimize the electron repulsions, is to assume a sp2 hybridization here for this carbon. So that is the trigonal planar geometry, and the carbocation is sp2 becomes sp2 hybridized carbon. This is an sp2 hybridized carbon. This is an sp2 hybridization. So when an sp3 carbon originally, like in this example, propane is sp3 hybridized carbon, due to some reaction it becomes, let's say it assumes the CH2, it loses an electron pair and becomes carbocation. During that time, in that transition, the hybridization changes from sp3 to sp2. So the geometry of that carbon changes from being tetrahedral to trigonal planar. So far what we did, let's summarize this. So we have looked at 2 different types of carbocations. What are they? The primary and secondary carbocations. We notice that since the number of electron pairs on that carbon changes from 4 to 3, from sp3 to sp2, the shape changes of that carbon and the bond angle changes. So we have a primary carbocation. So far we have seen a primary carbocation. An example is CH3, CH2, that's the primary carbocation. We have seen a secondary one, carbocation, which looks, so the central carbon has a positive charge. That means just to clarify, there's one hydrogen there. And there's something called a tertiary carbocation, as you'll see now. So a tertiary carbocation will look like this. A tertiary carbon, so which basically says is a carbocation on a tertiary carbon. So notice this carbon there, that is a tertiary carbon because it's connected to 3 different carbons. You have a tertiary carbocation. You cannot have a quaternary carbocation because when you say quaternary, the carbon is connected to 4 different carbons. So you cannot have a quaternary carbocation, but you can have these 3 carbocations. And then you can also have the simplest carbocation, which is CH3, which is the methyl carbocation. So you have a primary, in just the names of these carbocations are here. I'll put them in red, so just to know some names. I know we didn't talk about naming yet. So that's the propyl carbocation. This is the isopropyl carbocation, and this is the tertiary butyl carbocation. This is just the names, and we'll come to names later on. So here you have different types of carbocations, and apart from this, there are some other unique carbocations. Not unique. You can find many of them, but they look something like this. So you have a double bond, and then a CH2 plus. So notice one thing, that is the primary carbon because it's connected to another carbon, but this is different from this primary carbocation in the sense that this is a double bond next to it. So this is called an allylic carbocation. It's primary, but primary carbocation with a double bond next to it. And then you can have another special case where you have a benzene ring, and then a carbon on the benzene ring, and then a carbocation carbon on the benzene ring. So this is called a benzylic carbocation. So these are the things that we talk about in this first semester organic chemistry topics. So this is just the classifications of different carbocations and some special examples here. So in the next video, we'll look at the factors that affect the stabilities of these carbocations. We are very familiar with one factor that affects stability, which is resonance, and you can immediately see here the allylic carbocation can have a resonance structure which makes this stable. You can have a resonance for the allylic carbocation. Likewise, with the benzylic one too, you can imagine moving these electrons out of the benzene ring and stabilize the positive charge there. So we can draw a resonance structure where we can draw many resonance structures. I'm just drawing one. So this double bond, I'll just say carbon 1, carbon 2. Carbon 1, carbon 2 double bond move out of the ring to form a double bond with the carbocation carbon. So since carbon 1, 2 electrons moved away from carbon 2 gets the positive charge, and then the remaining two double bonds stay as such, and then we can draw the resonance structure. So this one is just this slide or this module capsule just brings us the different carbocations, and then, like I said, we'll talk about the three factors that stabilize carbocations. They are, just to name them, of course there's resonance here. In this carbocation, there's no resonance here, this one's here. But the other factors, which one is called hyperconjugation and the other one is called inductive effect. So we'll take them